So we talked about the importance of understanding far out of equilibrium dynamics, and we used condensed matter systems as our main motivation. I focused on two types of experiments. The first one is an example of the new type of probes, which have been common in condensed matter physics. We talked about resonant inelastic X-ray scattering and how one really needs to look at, to calculate the actual cross-sections for X, one needs to look at non-equilibrium processes. Then we talked about photo-induced superconductivity, and here we used examples, an example of experiments by Andrea Cavalieri, how by parametrically driving phonons, we can enhance electron-phonon interaction and thus lead to transient enhancement of superconductivity. We didn't really talk about strongly driven systems, such as, say, NV centers and diamond. Hopefully, you'll hear more about this from other speakers. Then I also mentioned ultra-cold atoms. So it looks like I actually will have more time than I originally planned. So we'll have some time to talk about the exploration of quantum many-body dynamics with cold atoms, something that I didn't originally sort of lay out in my outline. And what I emphasized is that this is a very challenging problem from the theoretical point of view. So let me just say a few words about the difficulty of understanding dynamics. So you can basically understand it by thinking about the size of Hilbert space that we need to deal with. So we usually talk about macroscopic bodies, right? Avogadro number of atoms, electrons. And when we talk about Hilbert space, we talk about sort of like space which is exponentially large in the number of degrees of freedom. So we're not just talking about large Avogadro number, we're talking about a number which is exponentially large in the Avogadro number. And this should be contrasted to, say, describing equilibrium systems. So when we talk about equilibrium, let's say especially in cases that can be described by, say, symmetry breaking or like Fermi liquid fixed point, actually even topological states, we can usually do very simple counting of the most relevant degrees of freedom, like Goldstone modes, or like Higgs-AMPLITUDE mode, and so on, or like vortex excitations, and we get a number of degrees of freedom which is only polynomially large in the number of particles. And therefore, when we talk about, say, small fluctuations around equilibrium state, we are really exploring just a tiny corner of the entire Hilbert space. But when we talk about far out of equilibrium dynamics, in principle, this can involve all degrees of freedom, like degrees of freedom at all scales, and they may couple to each other. And that's what makes dynamics such a challenging problem. And the method that we started discussing is to apply variational approach. So in variational approach, we introduce finite, again, degree of freedoms which scales polynomially in the number of particles, but it sort of exceeds the number of degrees of freedom which we need to describe small fluctuations around the equilibrium state. And the idea is that if we do the clever choice of variational wave functions, then we hope to capture all the essential physics of quantum many-body systems. So, OK. And one specific example that we're discussing is based on the idea of kind of Gaussian states. And that's something that should be familiar to you from your basic solid state classes. So if we go back to the superfluid phase of bosons, interacting bosons, you remember that it consists of two pieces. We have a condensate macroscopic number of particles in a state of the lowest kinetic energy plus quantum depletion. So we see that it's kind of something which is exponent of something linear in the creation operator and something quadratic in the creation operator. And then we also remember the BCS theory of superconductivity, That's the usual BCS wave function, which is a superposition of not having, like in a state of given momentum, we either do not have any particles or we have a pair of fermions with opposite momenta and opposite spins. And you can use fermion decommutation relation to actually write this as exponent of the quadratic form of the fermions. So that's something that we all remember from our basic classes. But the idea that we want to explore, which we started exploring yesterday and will continue exploring today, is that we can sort of generalize this class of wave functions while keeping this kind of character. And so what we focused on so far were bosonic Gaussian states, right? So we introduced notation of quadratures, right? So they're just linearly related to creation and annihilation operators, right? So think of x is equal b plus b dagger, right? And momentum is the conjugate variable. And then we said, oh, we can construct Gaussian unitary operator. And you can see that it has the same structure. There is a piece which looks like exponent of something which is linear in the bosonic operators, right? In xp, or which is the same, just linear superposition of creation annihilation operators. And piece which is quadratic in the bosonic creation annihilation operators. And then the coefficients here are, let's say, this delta of r, right, is really, as we saw, is just an expectation value, right, of quadratures. If we calculate the expectation value of x or of p in our Gaussian state, right, then it's given exactly by this coefficient delta. And then we can also calculate fluctuations, right, second-order fluctuations in the Gaussian state. And they relate, and so we have to define a couple more matrices, right? Like, so there is a matrix xi in the definition of the Gaussian operator and the Gaussian state. And then we define an exponent and then the square of the matrix. And that gives us the kind of fluctuations. And so Gaussian states are just like your kind of your usual Gaussian distribution. All the high moments can be expressed entirely in terms of two low moments, right? So if we're dealing with, let's say, if we're interested in correlations of the third order, they can be factorized in kind of linear and quadratic contributions. And what we also talked about is solving a very simple dynamical problem to begin with when we have quadratic Hamiltonians. So this allows for a constant force. So you see this is something which is linear in bosonic operators. In particular, it can be force times x, right? Just a force which is pushing our harmonic oscillator. Or it can be quadratic, for example, if you think about a mass on a spring. So the spring constant can change in time. That's something that's relevant, say, for our discussion of parametrically driven phonons. And then we discussed how to solve Schrödinger equation, right, time-dependent Schrödinger equation, using this Gaussian ansatz by basically taking coefficients of this Gaussian transformation to be time-dependent, and we derived explicit equations on the expectation value of the bosonic field, right? This is the coherent part, right? And then we have expectation value on the fluctuations on the squeezing part. Notice that in this case, this equation very nicely decouple, so we do not have any mixing between the expectation value of the bosonic operators and their fluctuations and the quadratic part. So in the case of quadratic Hamiltonian, this is the full story, right? You have time-dependent Hamiltonian. This is how you solve it. But then we said, well, we also want to analyze systems in which quadratic is more complicated, in which the Hamiltonian is more complicated. We have interactions between particles. In this case, we now use variational wave functions in particular. Like, say, we will focus on Gaussian ansatz for the time being, but we'll talk about generalizations later on. But the general philosophy of variational approach is to say, okay, I have some variational manifold, right, which is sort of shown as this curved surface. And then we have to take the usual Schrodinger equation. But generally, if we think about the evolution of my wave function, right, a change in the wave function described by h times psi will take me outside of the variational space. Right? And what we want to do is we want to take this small variation of the wave function and project it back onto the variational manifold. And the way it's done is by defining a tangential plane, right? So I'm saying, OK, this is my instantaneous state, and then I can define basis vectors, right, in this tangential plane. And then if I have a small, when I calculate a small change in my state vector, right, I have to take projections of this general change of the wave functions on the basis vectors, right? And the basis vectors I construct just by asking, OK, how does my many-body wave function change if I change parameters in my variational space? Well, the price that you pay is that generically this, not the price, but let's say one difficulty may be that the states may not be orthogonal, so you have to use Gram matrix. But actually, in examples that we will discuss, this issue will not arise. So a physical way of thinking about Gaussian ansatz then is the following. So think about this way. So we have some instantaneous state, and generic Gaussian state can be thought of as sort of kind of Bogoliubov state, right? You know, Bogoliubov vacuum as compared to the vacuum of bosons. Again, think of here just BC of weakly interacting bosons. So we know that we can go from original bosons to Bogoliubov excitations, right? And so the Bogoliubov state is a vacuum of these Bogoliubov excitations. So we're in a state which is a vacuum of Bogoliubov excitations. And then we can express any operator in terms of these Bogoliubov operators, right? And then what we're basically keeping when we using Gaussian dynamics, we're only keeping terms up to second order in these Gaussian fluctuations. Right? So we just truncate all the terms of higher order. So again, it's not the same as just keeping terms up to second order from the point of view of the original vacuum, right? Because we're actually, like when we have a condensate, right, we have an infinite number of particles. It's really just up to 2 excitations on top of the instantaneous state. So, and now, of course, instantaneous state keeps changing. OK, and then we also said how to derive equations of motion for parameters of the Gaussian ansatz. So if we have a more complicated interacting Hamiltonian, they actually look very similar to what we find for quadratic Hamiltonians. We still have the same evolution sort of the coherent part, of the squeezed part. But now the coefficient, right, are no longer coefficients of a fixed quadratic Hamiltonians. They actually need to be obtained by taking the expectation value of the interacting Hamiltonian in the Gaussian state. And this expectation value, of course, generically depends on both the coherent part and the squeezed part. But once we have this expectation value, then we can easily obtain, take these derivatives, and this will allow us to then keep track of dynamics. Yeah, questions? Right, and of course it's...
Can I have a question?
Yeah.
It looks like in this formulation, the equations are in fact integral differential.
All the differentials are not even integral.
But you have to self-consistently insert these averages of the Hamiltonian.
That's right. They're nonlinear, but they're differential in time.
And
of course, there is like summation in momentum, if that's what you mean, right? Yes, in that sense, they're integral. That yes, you have to sum over momentum generally. Yes. But fundamentally, you know, like I actually, I just think about this. Let's say gamma is just a giant matrix where k is one of the indices, right? Therefore, what we have, this expectation value of h is just functional of the matrix gamma, right, and vector delta. And so, therefore, this equations are obviously nonlinear equations. They depend on nonlinearly on, let's say, both the coherent part and the kind of the quantum squeezing part. Okay, other questions? Okay, and another aspect that is very that will come in very usefully to us is that, you know, to start dynamics, often you want to start it from the ground state of the system. So we want to be able to calculate ground state, and we actually formulate the problem of finding the variational ground state as also a kind of dynamical problem. So what we said is, well, let's look at the evolution of arbitrary initial state, but now in imaginary time. And then, as we discussed, so generically, because look, as if we keep, if we decompose the initial state in terms of eigenstates of the system, we see that they will different contributions will decay exponentially in time, you know, with the rate determined by the energy, and of course the ground state will decay most slowly just because it has the smallest energy, and therefore if we take the limit of tau going to infinity, the important contribution that will stay will be just the ground state contribution. And so once we accept this idea, then we said, oh, actually, then to find the kind of the long imaginary time limit, all we have to do is just solve, formulate it as differential equation on the state, but not in real time, but in imaginary time. Right? And this is kind of very simple equation that we get. So basically, you can more or less operate with sort of equations for finding the ground state the same way as we operate with equations for imaginary, for real-time dynamics with very minor differences. Okay, so now let's switch to fermions, right? So we understood how, so I also talked about example of bosonic Gaussian state. It was for Ehrlich-Polaron. Now let's sort of first develop formalism for fermionic Gaussian states and then apply it to one specific problem, which will be a famous Kondo model. Okay, so this is, let's set up some general formalism. So it turns out that for just technical reasons, it is continuous. So it's convenient to separate the usual Dirac fermions described by sort of annihilation and creation operators into Majorana fermions. Right. So it doesn't mean that we expect to have real Majorana excitations in the problem, although we might find them. This is just a technical trick just to make sure that like matrices that we'll be calculating, they will be real. So if we have any fermionic degree of freedom, right, J, then we can decompose it into basically take the sum and the difference of the two, and now you can very easily check that, let's say, these Majorana fermionic operators, the Hermitian conjugate of themselves. Then if we take different Majorana fermions, they anti-commute, but the square of Majorana fermion is 1. Right? So therefore, basically, we will just operate with these Majorana fermion operators, and this is the key anti-commutation relations. Okay, and then we will also arrange fermions in sort of like a vector notation, since every fermionic degrees of freedom, right, gives rise to 2 Majorana fermions. If we start with n fermionic state, then this kind of Majorana fermion vector has 2n components. But let's say we can always go back to the original fermions, let's say to creation annihilation operator. It's just by sort of multiplying this Majorana fermion vector by another matrix. Okay, so I will not go through the details of the derivation. Actually, they're very similar, to what we did for bosons. Just instead of commutation relation, we need to use anti-commutation relation. So I'll basically just state the results. So again, define a Gaussian transformation, and remember that for fermions we cannot have operators which are linear in fermionic operators, right? So basically, we cannot mix states which have different parity, and that's why we sort of in the Gaussian part, the only contribution that we have, right, is quadratic, right, in the fermion operators. And so you can think about this operator as something that generalizes Bogoliubov transformation. Just recall that in our usual BCS wave function, right, if we take psi BCS, it's a product over k, u of k plus v of k. On the vacuum, and then we know that to construct actual excitations, we have transformation which look like u of k, say c of k up plus v of k, gamma minus k down, dagger, right? So these are rotations which transform the vacuum of the fermions into vacuum of Bogoliubov quasi-particles, so to the BCS state. So basically, you can think about this matrix this matrix psi as accomplishing the same rotation. So we can show that if we apply this unitary transformation on the Majorana fermion, right, we rotate between different components of this Majorana vector, right? Just like in the case of the BCS wave function, right, we rotate between creation and annihilation operator, right, spin up and spin down. This is just a more general version of this. We can now mix different momenta, mix whatever internal states we have in the problem. And you can see that the structure is again very similar, that this rotation matrix is just exponent of the matrix which we have in the Gaussian transformation. So one difference is that in the case of bosons, because bosons commute, the matrix was symmetric, but now this psi, this Majorana matrix psi, has to be anti-symmetric. Okay, right, and then what? The way as we said, we define the Gaussian state is we just take a vacuum and then we apply a Gaussian transformation, right? And so then in this Gaussian state, if we want to calculate like expectation value of Majorana fermions, we will get this covariance matrix, and covariance matrix is again quadratic in that Bogoliubov rotation matrix. And again, I remind you that we cannot talk about expectation values of the A operator itself, right? A operator is something which would be linear. So A operators are linear in creation annihilation operators. We cannot have expectation values of fermionic operators, right? We can only have expectation values of squares of fermionic operators. So this covariance matrix really contains all kinds of expectation values, right? You can think it contains expectation value of, let's say, this type, contains expectation value of this type, right? And obviously this type. So they are all encoded in this covariance matrix, which has dimension 2n by 2n. Okay, so I'm just throwing these formulas again without going through the derivation, but you can see that the structure is very similar to bosonic case that we discussed before. And so, okay, it would be somewhat tedious to go through it again. Right, okay, and that's what we said, that this anti-symmetric, and in fact, like in this specific case, we are looking at just pure states, so this formalism can be generalized to, let's say, thermal states, but we'll not talk about this. So in this case, you can also easily prove that gamma squared should give a kind of unit matrix with a minus sign. Okay, any questions? Right. So, okay, okay, and let's say, as we said, that if we have expectation value of this Majorana fermions, then we can construct, any of the expectation values of the Dirac fermions if we want, like, say, occupation number, which is C dagger C, or we want anomalous expectation value C dagger, right? They are all contained in here, and they can be related. This is just by remember, we talked about rotation between C operators and A operators, Majorana fermions and Dirac fermions. So that's how we can easily get expectation values of, in terms of Dirac fermions. OK, and then actually you can do the same arguments for calculating variational dynamics. You give me a complicated interacting Hamiltonian, but I I make an assumption that I can describe it as a Gaussian state, right? And often what you remember is the simplest Gaussian state is a Slaty determinant, right? You just choose a certain number of single particle orbitals and you put n fermions into the single particle orbitals in a way that's perfectly antisymmetric. Generalization of the Slaty determinants is, say, the BCS state. So this just involves a kind of Bogoliubov particle-Hall transformation. So all of them are just examples of the Gaussian state. So it's a fairly rich class of wave functions. And if we want to write, if we're looking at some non-equilibrium problem, say, where Hamiltonian is changing in time, or like it was suddenly changed in time in the case of a Quench, we can write differential equation on this covariance matrix, which will involve a commutator now of the covariance matrix with some effective Hamiltonian. But this Hamiltonian for an interacting case is just derivative of energy with respect to covariance matrices, just like for bosons. So your main challenge is really calculate expectation value of the interacting Hamiltonians, of the interacting Hamiltonian in this kind of Gaussian state using covariance matrices. But once you have this expectation value, the rest is just a simple, solving simple differential equation. OK, and then we can do the same thing in imaginary time when we're interested in the ground state. Again, so the form of the equation is slightly different, but the main idea is the same. We just have to be able to calculate the derivative of energy with respect to covariance matrix, and then we can look at the evolution of the covariance matrix in imaginary time and just wait until it reaches the fixed point. OK, any questions? So this was kind of a very quick overview, but I hope you at least get the idea, and then you can find the details in the paper. OK, so as I said, just to convince you that this is a useful technique, let's look at the Kondo problem. So the Kondo problem is, of course, has a long history in condensed metaphysics, and people use very powerful tools for solving it, normalization group or DMFT. So we have experts, Alexei Tov and Sasha Lichtenstein, who sort of developed very special tricks for solving quantum impurity problem. I'll tell you on sort of like how we sort of came up with another way of solving this problem, which I think has its advantages. In particular, it seems very useful for looking at non-equilibrium dynamics. OK, so let's start by defining the Kondo model. So the Kondo model is maybe it's written in a somewhat unusual way here, but I remind you that the Kondo model has just the three fermions, right? And it has interaction between one localized spin, right, with the spin of fermions, right? Say r equal to 0, if sigma alpha beta, say beta of r equal to 0. So it's really just local interaction, local exchange interaction between itinerant electrons and a localized spin. So here we write it in a somewhat more general way because we may be interested in say systems with disorder. So this is a quadratic part, right? This is what we call free fermions, although it doesn't, like free means it's just quadratic. It may involve some kind of, I don't know, finite size effects, disorder, and so on. Reduced like quadratic traps in the case of cold atoms. Then we have interaction between the impurity spin and the spin of the fermions. Now we introduce something more generic. You can see that actually we do not insist on the interaction being sv2 symmetric. In fact, I will show you examples when we go away from the symmetric point. And OK, so here we also, in principle, we may also couple, it may be an extended Kondo model. So here, like in the conventional Kondo model, we only have coupling to fermions at just one point at the origin. Would say in some of the questions that we're addressing, we're dealing with, say, Rydberg systems in ultra-cold atoms, in which case you have non-local interaction. That's why we have something which is more generic. So it's kind of a generalized version of the Kondo model. So, OK, so what one knows is that the key to the Kondo problem is the formation of the Kondo singlet, that the impurity spin is very strongly entangled with an itinerant electrons. That's why, simply throwing, mean field ansatz on the Kondo problem would not work. So we have to do something more clever. And in fact, what we do is in many ways inspired by this Lilo-Pines transformation that we discussed before in the polarons. So basically, we want to use conservation laws present in the system in order to get rid of the impurity degrees of freedom. So in this case, let's say I allow only magnetic field along the z-axis. I have a symmetry of rotations around the z-axis. In fact, I really need just symmetry of rotations by pi. Right? So I know that if I rotate my system by pi, the system goes into itself. Right? And as you will see, this allows to make a precise transformation which completely decouples impurity, which makes the impurity a classical variable. So let me take you through the main steps. So we define this parity transformation, right? It's a product of the component of the impurity spin times parity operators for spin-up fermions. So you can see that this parity operator, if it acts on a state where I have even number of spin-up fermions, I get +1. If I act on a state that has odd number of spin-up fermions, I get -1. So this operator is actually conserved, right? It commutes with the Hamiltonian. And you can also see if I square this operator, I'll get 1, right? Therefore, it's an operator which can have values of +1, -1, right? When it's squared, is equal to 1, and it commutes with the Hamiltonian. So how do we see that it commutes with the Hamiltonian? Well, let me rewrite it in a kind of more convenient way, or convenient for seeing this. First of all, let me remind you that we can use Pauli matrices to write sigma z, right, of the impurity as just exponent of I pi half of sigma z impurity. And then you remember that this is exactly the operator of rotating the impurity spin by pi. Therefore, this operator, right, the sigma z itself is nothing but rotation around the z-axis by pi. And 1/2 just comes, because the spin is 1/2 times Pauli matrix. On the other hand, if I look at this parity operator, e to pi and up, I can just sort of write it as a sum of two contributions where I have an up minus and down and an up plus and down. So an up plus and down, just the total number of particles, that's conserved. So that clearly is commutes. And what I have from an up minus and down, again, you can see pi over 2 times an up minus and down, but that's just sz of my fermions in the bath. Right? Therefore, you can see that this pi half times an up minus and down is, again, an operation of rotation by pi of the fermions, like in the bath. Therefore, the two terms together actually correspond exactly to rotation of the system as a whole by pi. Right? And we know that the Hamiltonian is invariant, like this system is symmetric if we rotate the Hamiltonian by pi. OK, so we have an integral of motion. And again, I remind you how we can utilize an integral of motion. So our idea is, like in the Lilo-Pines transformation, was we know that the total, like it was a problem of a polaron of impurity in a bosonic system, and you know that the total momentum was conserved. So what we did was to make a transformation which mapped that conserved total Hamiltonian into the momentum of the impurity. After that, we said, oh, now momentum of the impurity is conserved, right? Because it really comes from the original conserved quantity from the integral of motion. And once a momentum of impurity is conserved, we can treat it as a C number. So we want to do the same operation here. We say, well, actually, this parity operator, which has eigenvalues -1 and +1, and squares to 1, is kind of like a spin operator for the impurity. Right? If you take any of the spin components of the impurity, we know that it has eigenvalues, well, ±1/2. OK, this doesn't matter. You can always multiply by 1/2, and it squares to just 1. Therefore, it's interesting to ask a question, well, can we actually come up with a transformation which maps this parity operator, which we know is an integral of motion, into one of the components of the spin? It doesn't matter. Well, OK. Well, usually it doesn't matter which one. And the answer is yes, you can actually do this. And in fact, you can construct this operator. It's a unitary operator. Right? And it's now, again, we use this PZ. So this was parity operator for fermions in the bath. Right? And the sigma y is now rotation matrix, Pauli matrix for the impurity spin. So this can also be, as we said, sort of going to the impurity frame, sort of going into a frame rotating with the impurity spin. OK, so let me just demonstrate this, that if we take this total parity operator, we apply this unitary transformation, we will get exactly the x component of the impurity. So I'll just sort of show you take you through some of the key steps. So it's kind of a matter of very simple algebra. You remember that PZ operator, right, only acts on the fermions in the bath, right? And the sigma is what acts on the impurity spin. So let's, and our, right, P total, so we have operator P total is sigma z times PZ, and PZ is e to I pi and up. Right, so we want to see how this operator transforms under this unitary transformation. So let's just take different parts of this P total operator. Let's take sigma z impurity. OK, we sandwich it between U dagger and U. Obviously, OK, PZ commutes with sigma z. So we just have to think about a commutation relation between y and z components of the spin. Right, so we just do it brute force, just open it up. Let's say we keep the terms of 0th order in PZ. Right, so then we just have the sigma z in the middle. Then we take the term which is linear in PZ, right? And then we have one contribution with sigma y, sigma z, which is this one. Another contribution. Now it's like 1 on the left and sigma y PZ on the right. And so this you can see together the two combine into a commutator of sigma y and sigma z. Then we have a contribution which is quadratic in PZ, right? And now we have 3 Pauli matrices, sigma y, sigma z, sigma y. OK, so now we know the commutator, right? We can take the product of 3 Pauli matrices, and you see that it ends up being just sigma x of the impurity times PZ, right? So that's just, the algebra of Pauli matrices. And now we sort of have to look at how the parity operator transforms. Now the parity operator commutes with operators which correspond to the impurity spin. But we should remember that PZ squared is 1. So again, just sort of doing this operation, we see that, so PZ, we get Pauli matrix squared, which is 1, right? And we get this parity operator cube, which is the same as parity. So it's just parity. So therefore, OK, we derived that's a transformation of sigma z of the impurity, transformation of the parity. So then now we can write the transformation of 2 of them together, and it's sigma x, right? So what this shows us that this is a transformation, right? Rigorously maps the parity, conserved parity operator into x component of the spin of the impurity, which will guarantee that after we make a transformation, sigma x of the impurity, will be fixed. It's a C number. The impurity will no longer rotate. Huh?
It's time for break.
Just give me a few minutes. Yeah. So now what we can do, we can just sort of continue we can transform the entire Hamiltonian, right, using just very simple rule. Like again, we want to use parity. So we want to use this unitary operation U, right, which we defined here. And in the Hamiltonians, only non-trivial transformation involves the fermions. Let's say really spin up fermions, and the parity operator will give us a minus sign. OK, so now I'll just leave you, I guess, with this. Right, that if we apply this transformation to the Hamiltonian, so this is what happens. See that what's left from the impurity spin in this Hamiltonian is just sigma x. We no longer have sigma y. We no longer have sigma z of the impurity, which means that sigma x now commutes with the Hamiltonian. That's exactly the statement that it is conserved. Right? So we did rigorous transformation. And at the end of this transformation, so we decoupled the impurity spin. It's a C number. Well, is it free lunch? Well, it's not free lunch, because notice the Hamiltonian now contains this p bath. So I changed the notation. This p bath is this parity operator, right? It's exactly the same pz operator which we defined here. Right, so it's something which is exponential in the quadratic, in the square of fermion operators, right? So this is e to I pi sum over all n, c n up, dagger c n up. So the price that we pay for integrating out the impurity spin is that we get a kind of much more complicated interacting Hamiltonian. You can see that it contains now infinite order interaction, like basically because it's exponent, when you open up, you have interaction of infinite number of fermions, right? And it's infinitely long ranged. And so if we want to use it for some kind of analytical treatment, that's not the most convenient form. But for variational treatments, actually, it works, as you will see, quite nicely. So let's take a short break. OK, let's continue. We did transformation of the generalized Kondo Hamiltonian. And as we said, the key aspect of this transformation is that we decoupled the impurity spin, because now sigma x is a conserved quantity. And we can choose it to be either +1 or -1. And so what we're left with is a problem of interacting fermions. This is kind of a strange interaction. It's infinitely long range. It's sort of beyond the usual two-particle interaction. But if we apply variational approach, it actually doesn't matter how complicated interaction is, as long as you can compute expectation value of the Hamiltonian in the Gaussian state, you're in business. And that's actually how it works. OK, I'll not go you through the take you through the calculations. It's sort of you end up with things like Pythians of this covariance matrix and so on. But you can express, like you have an explicit expression for the energy. And now you can, let's say, look at dynamics in imaginary time to find the ground state, or look at dynamics in real time to find non-equilibrium dynamics, right? So that's, remember, our usual trick. That's what we discussed before. Just to find the ground state, just calculate this evolution in imaginary time, find the fixed point, and or look at the real-time evolution. So, OK, let me show you the results. And maybe before I start discussing numerical results, let me remind to those of you who forgot about Kondo systems some of the key facts. So a very remarkable feature of the Kondo problem is that it's non-perturbative, right? So if we take this Hamiltonian, in fact, we generalize this to have Jz and J-perp. So J-perp would correspond to Sx and Sy components of the interaction, right? So this is J-perp, this is Jz. So usually the best way to understand the phase diagram is to use renormalization group approach. It's basically an idea as you lower the temperature, you try to ask how do parameters of the Kondo Hamiltonian scale, and you find that if you're on the antiferromagnetic side, all J's are positive, then we find that all the J's sort of flow towards strong coupling, right? Which means that no matter how small J is, and in real solid-state systems, J is typically small. So naively, you'd say, oh, I can treat it by perturbation theory, but you actually find that perturbation theory breaks down because at low enough temperatures, J will grow to become a relevant perturbation. But then if we're on the ferromagnetic side, actually, it really matters whether we have easy axis or easy plane anisotropy, because if we have easy axis anisotropy, then the RG flow, or like in the case of SU2 symmetry, we basically flow to weak coupling. So J's become very small, and this means that basically impurity spin decouples. On the other hand, if we're in the easy plane regime, then even though we start we start with all the J's being negative. We start in the ferromagnetic regime, and so first the system kind of flows towards smaller J, as if they want to become irrelevant, but then eventually it will turn around, and so the end result will still be a singlet formation, right? And that's kind of very surprising. So usually when we talk about solid-state systems, we're only concerned with antiferromagnetic regime. So actually, our motivation for looking at Kondo really came from cold atoms. It turns out that in cold atoms, you are interested in this kind of anisotropic ferromagnetic regime, right? And you can see it has actually much richer structure because depending on if you can tune anisotropy, which you can in cold atoms, you can even find this very surprising crossover when you start with ferromagnetic regime, but at sufficiently low energies, you will recover the antiferromagnetic behavior. Okay, but so what we do now is we just run dynamics in imaginary time of this Kondo Hamiltonian, this transformed Kondo Hamiltonian, and we want to check different regimes. So one regime, okay, that's the conventional antiferromagnetic regime. And in order to test what we're actually getting, what we're calculating is correlations between the impurity spin and the spin of electrons at the position of the impurity, right? Basically, we're asking, we have an impurity spin and the spin of the electron, so are they pointing the same way or are they pointing the opposite way? Well, okay, and that's what's shown here. So this is a triangle, so you see minus, I mean that they're anti-correlated, right? Okay, that's what we expect. It's antiferromagnetic regime. Then there is this blue regime, right? So this is ferromagnetic case. So that's where we expect the impurity spin to be correlated in the same way as the fermions in the bath. And indeed, when we find the fixed point, right, we find ferromagnetic correlations. And on the other hand, if we start with a ferromagnetic Hamiltonian, but in this easy plane regime, then when we look at the correlations in the fixed point, they actually become antiferromagnetic. So this simple kind of Slaty determinant actually knows about the true Kondo ground state, this non-perturbative ground state. And in fact, actually this this plot has more information. It shows how correlations evolve in space, and indeed it sort of it shows this expected oscillations. Then you can do some tests. For example, you can look at let's say again static correlations, how they behave, and so you know from basically exact solutions of the Kondo problem as well as numerics that the correlations should go as 1 over x at short distances and then 1 over x squared. That also comes out from our variational calculations. We can also see that there is this emerging Kondo scale, so we can basically see how this basically the appropriate, so because here very different parameters can be scaled to the same universal form of the correlation function, right, in terms of just one length, and we know that there should be an emergent length scale, which is a Kondo length, and this Kondo length should depend exponentially on the microscopic interaction, and indeed this all sort of comes out of this variational analysis. So in fact, we were curious to even, let's say, do like quantitative comparison. As a golden standard, we took matrix product state, and actually, so here you can see that, like for the static problems, you can't see the difference between matrix product state, which is more or less exact solution, and the variational calculation. Okay, and as I said, actually, since our interest came from cold atoms experiments involving dynamics are much more natural. So what the type of quenches that we considered, so the type of dynamics that we considered were really quenches. When you have an impurity spin which was originally decoupled from the fermions, and then you suddenly switch on the coupling. Right. So, and then you ask, how do correlations between this impurity spin and the Fermi bath develop in time? So, okay, I will not talk about how to realize this system in experiments. Again, if people are interested, I'll be happy to explain later. So this is just results of, let's say, calculations, like looking at time evolutions. So, okay, let's start from the regime, okay, let's say one, which is ferromagnetic, right? So we have an impurity spin, it's uncorrelated like spins are uncorrelated to begin with. So impurity spin is uncorrelated with the fermions. And then as we switch on interaction, you see that on side, like locally, we develop blue correlation. Blue means positive ferromagnetic correlations. So kind of like a fermions adjust their spin to the impurity spin. And of course, what this means is that, let's say, if we locally create a spin up, then we have an imbalanced spin down, which has to be sent away. So you see this kind of wave of the opposite spin kind of traveling with the Fermi velocity. Then we take regime 2. Right? So in the case of regime 2, like, so now we actually want to develop anti-correlations with the impurity spin. So if we have, let's say, the impurity originally with spin up, so we have to locally polarize fermions with spin down, right? And of course, they'll make a thing that they start rotating, but still, we somehow, once we we have to locally build up spin down so that we can, together with the impurity spin, take it up to a singlet. And that means that we have an extra wave of spin up being sent to infinity. Right? Again, this is something that we can see. And then regime 3 is most interesting, right, which has this crossover from the ferromagnetic behavior at kind of high energies or short times to anti-ferromagnetic behavior at long times. Here the dynamics is rich. You can see that at short times, just as we expect, because our original Hamiltonian is ferromagnetic, the impurity spin develops ferromagnetic correlations, right? You see this kind of blue. But then after some time, the system kind of like in real time discovers this RG flow, and it's not clear why, equilibrium RG flow should agree with real-time dynamics, but it looks like, yeah, real-time dynamics is mimicking this RG. So after some time, the system switches from ferromagnetic correlations to anti-ferromagnetic correlations. And okay, I'll not talk about, like, so this is also something like we compared dynamics with matrix product state. It works quite well. And of course, the difference is that we have orders of magnitude fewer parameters. So calculations, instead of taking hours and days, just take minutes. So any questions?
So for temperature equals 0, or
so far, let's say I'm showing you only it's a very specific initial state, right? It was 0 temperature. I'll not talk about generalizations to finite temperature. We have some results already, but I'm not going to show them.
The finite temperature would be even better.
It's a long story. I'll be happy to talk to you separately about what we find at finite temperature. Actually, it's somewhat more subtle. Okay, so again, I will just throw in an idea. I don't want to go into the detail. You can take this idea even further. So actually, the Kondo problem arises from an even kind of more microscopic model, which is a so-called Anderson model. So it's basically a model of an impurity atom in the sea of fermions. So it's a model in which you have 3 fermions. you have the d orbital, right? It's an orbital on this impurity particle, right? And it's chosen to be such that the d orbital is below the Fermi energy. But we have strong repulsion on this d orbital, so that if we try to put two fermions on the d orbital, then okay, we would find a state which is way above Fermi energy, so we end up with just single occupancy, and that's the free spin. So now this impurity problem has more degrees of freedom because we can have, let's say in the Kondo problem, we only have spin up and spin down, just two states. Now we in principle have to keep track of 4 states, kind of empty, 2 single occupied states and 1 double occupied state. But it turns out that there is a generalization of this parity transformation, which allows to basically diagonalize this impurity site so that you get effectively a Slater determinant which just describes the fermions. It's basically like integrating out the impurity problem. And so I'll just show you the results. So now we can calculate the spectral function of this Anderson model. So basically it's a spectral function which you obtain from a single Slater determinant, and it has this emergent Kondo resonance. It also has, okay, so this is peak which corresponds to the original d level, d plus u. And actually there are some kind of features which people usually don't think about, which have to do with, like some special states at the bottom of, it's kind of high energy features at the bottom and top of the band. Anyway, so this is just to show you that it's kind of interesting that very subtle effects, which usually require very sophisticated, theoretical tools, appear to sort of can be captured, at least technically, with a single Slater determinant if you do the right trick, which is this decoupling transformation. So again, to kind of wrap up the discussion of the quantum impurity problem, the main challenge, right, of this quantum impurity problem is entanglement, right? Because we realize that the impurity degrees of freedom are really entangled with the bath. That's why trying to do Gaussian ansatz on the Hamiltonian as is would not work, because it doesn't give us the right entanglement. However, if we come up with the right transformation, right, and in this case the transformation was, like say in Kondo, it was just utilizing parity operator. That transformation has enough entanglement in it that even though after the transformation we use a Gaussian wave function, from the point of view of the original degrees of freedom, we actually have enough entanglement to capture the essential Kondo physics and Anderson impurity problem physics. And so again, just to emphasize what this means is that, remember, after the transformation, the wave function that we take, so after the transformation, right, our many-body wave function is basically, let's say, sigma x equal to +1 or -1, right, for the impurity, and some Gaussian state for the fermions. So you can see that it's a wave function which is factorizable between fermions and the impurity spin. But it doesn't mean that the original wave function is factorizable, you see, because this is after this transformation which utilizes conservation of the parity. In terms of original degrees of freedom, we actually have very strong entanglement between the impurity spin and the fermions. Okay, any questions?
Have you tried different values of u for these atoms? I wonder if you can see a crossover from metal to this, say, Kondo regime.
I think so far we only used sufficiently large value of u because we were really trying to test and recover the Kondo peak. But yeah, obviously it would be interesting to explore the whole range, like mixed balance and so on. Actually, also it's worth mentioning that so there are generalization of this also from one impurity to two. So if there is any interest to solving, let's say, 2 Kondo, so you can actually exactly decouple 2 Kondo spins from the bath and do the same analysis. Unfortunately, we don't know how to do it for more than 2 Kondo impurities, so we cannot really solve, let's say, Kondo chain, which would be very interesting.
Kondo triangle would be interesting.
Okay, so what's special about conduct triangle?
The overall spin is odd.
Mm-hmm.
So well, basically it's frustrated system.
Okay.
You have two, they are antiferromagnet.
Sure. Yeah.
You have three, they don't know how to order.
Okay. Yeah. Okay. Interesting to think about it.
And other question, this figure, if you look closer, you have some oscillations which are
It's
probably
probably
artifacts.
finite size. Yeah. Because wasn't very large system with like 30 or 40.
How hard would it be to enlarge system to get rid of them?
If you're a professional in numerics, it would probably be easy. But since we're not,
I see.
because it's really basically, it's not using any clusters, or any supercomputers. It's just like MATLAB and your laptop. Now let's talk about electron-phonon systems. Because remember I started with the original motivation to let's say try and explain photo-induced superconductivity, and along the way I already showed you some of the results for non-equilibrium dynamics of electron-phonon systems, such as the emergence of the Higgs oscillations. So now let me just give you some of the steps or kind of the ideas which went into variational calculation, which I showed you, which demonstrated, let's say, Higgs oscillations. So first of all, okay, what's the microscopic model? So as I said, we sort of take a very simple microscopic model, Holstein model, right? So we don't put any special details of electron-phonon interaction. So we just have some bosons with some dispersion, fermions, and local coupling between bosons and the fermions. And okay, so we have a technique, right, of just Gaussian wave functions, but just throwing in Gaussian wave function again on the Hamiltonian as is wouldn't be so good, because if so we talked about Gaussian state for bosons, Gaussian state for fermions. If you want to make a combined Gaussian, well, then it would be a factorizable, right? So the wave function would be a Gaussian state for bosons times a Gaussian state for fermions. But if you factorize electrons and phonons, you cannot capture such subtle things as superconductivity, the fact that fermions can exchange bosons, which then can exchange a phonon, which then mediates superconductivity. So there is entanglement between electron and phonon degrees of freedom, which we really have to capture. And that's why we have to broaden our class of wave functions. We have to go beyond Gaussians. And the idea, as we discussed yesterday, is to consider some kind of Polaron transformation, right? So you can think about it as basically a shift of bosonic variables, right? Remember, let's see, if I just use this P, right, for boson, that's something that corresponds to just shifting shifting the x or displacement of the phonon degree of freedom in a way that depends on the fermion numbers, on the fermion distribution. And what's different about what we are doing and Polaron transformation that have been studied before is that parameters of the Polaron transformation are not fixed. Usually people just do one Polaron transformation with some values of lambda, then just stick to this value of lambda and work with the mean field kind of Hamiltonian. But clearly we expect is that there should be much richer dynamics. In particular, that there was, if you recall our discussion, if we, what this Polaron transformation does, it induces effective electron-electron interaction, right? This is a mattress effect, right? If you have one electron, it distorts the phonons, right? It creates kind of basically an ionic distortion, and then it's a screening cloud, and then the screening clouds attract the second electron. So you want to actually maximize this lambda to maximize this effective interaction. On the other hand, if we take larger lambda, we have kind of stronger polaronic dressing of fermions, like hopping becomes harder. Again, let me, if you recall, so I didn't put it on a slide. If we think about effective hopping, right, when we were J effective, right, so it's, sorry, we can call it T effective, right? It basically becomes beta T, and but it will have terms which go lambda V minus B dagger, right? And so if I take large lambda, then it means that I'll get additional suppression of the hopping. And that, of course, penalizes kinetic energy. And if we're looking at sort of very non-equilibrium state, you can imagine that the system adjusts, right? Like it doesn't want to have the same sacrifice, of interaction versus kinetic energy in the low energy sector and the high energy sector, right? So therefore, if we want to keep it as a free parameter.
I have a simple question. Why does the usual Gaussian ansatz not include superconductivity here? The
just doesn't.
State is also a Gaussian one.
If you have an explicit electron-electron attraction.
Yes.
In this problem, I don't have explicit electron-electron attraction.
But there is a term which couples bosons and fermions.
That's correct. So that's why I have to, usually the way we do it now, you first derive BCS Hamiltonian, and then you do mean field. Right, but I want, like, if you do this, then you're sort of making certain assumptions about the state of phonons. That's how, like, traditional BCS theory works. You integrate out equilibrium phonons, you get your BCS Hamiltonian, and that's what you use. But, we're interested in very non-equilibrium state of phonons. So, in essence, like, I want to see what my phonons, if I'm driving them, my effective electron-electron attraction changes, but also because phonons are out of equilibrium, they start scattering electrons more. So I want to put much more physics than the usual BCS Hamiltonian. So you're right that BCS Hamiltonian is mean field, but in order to do this mean field, you have to start with explicit electron-electron attraction. And in order to generate, I have to entangle, because you see the usual, like, kind of how this kind of second order processes that we discussed last time, this is a form of entangling of electrons and phonons, right? Because electron emits a phonon, which is then absorbed by the electron. It's like Schiffer-Wolff type transformation. Good. Other questions? Okay, so now let me give you the general framework. I'll spare you again details. So now variational wave functions, they have now this kind of entangling transformation. In our case, like in this case, this happens to be polaronic transformation, but actually this, like in other problems, this is a more general class of ansatzes. So, and then it's followed by taking a Gaussian wave function for fermions and bosons, like in our case, phonons and electrons. So, like at this Gaussian level, right, the wave functions factorize between electrons and phonons, but they are first entangled through this polaron transformation. And what we want to do is project our Schrödinger equation, right? We want to take time derivative of this wave function is Hamiltonian acting on the wave function, but again, we have to use this trick. If we apply just the Hamiltonian, it takes us outside of the space of our variational wave function. We have to project it back into our class of wave function. So, okay, not sure I want to. Okay, I'll just give you a flavor of what we want to do, right? So when we calculate, remember when we calculated the time derivatives, right, of operators, we have to be careful about the fact that, let's say the time derivative of Gaussian, say, doesn't have to commute, doesn't commute with the polaron transformation, and vice versa. The time derivative of the polaron transformation, right, doesn't commute with the Gaussian part. Therefore, there is some kind of so when we take time derivative, obviously, we just generate time derivative of the transformation itself. But we have to rearrange, we want to rearrange everything. I want to rearrange everything in such a way that when I calculate the time derivative, I still have, this basically the same type of polaron transformation in Gaussian on the left and also time derivatives on the right, kind of acting on vacuum state. And what we will have to do is then dress this time derivatives by sort of dressing by, say, Gaussian transformation or the symmetry transformation. Well, let me just maybe explain one of the terms, right? So think about this term. So first of all, you see I have U Gaussian and U Gaussian dagger, right? Well, actually, because it's a unitary operator, the two will cancel. Now look at the operator. All right, it's time derivative of the Polarn transformation, but it has the Polarn transformation dagger. So if this multiplies this kind of Polaron on the left, so the two will cancel. Therefore, what I'll be left with is just time derivative, right? And indeed, that's what we expect. We want a time derivative on the left, right? So that's kind of the logic. Anyway, but once we write this, then we have a Hamiltonian, and in the Hamiltonian also acts in principle on the left, right? It acts on the wave function, but I want to move it on the right. And so what this means is that I'll have to consider a Hamiltonian in which is kind of has a Gaussian transformation and has Polaron transformation in it. So why do I want to do this? Well, because I want, my operators acting on vacuum, right? Because it's very easy to act on vacuum. I know that I can create excitations, but I cannot annihilate them. And in fact, so it turns out that, we can do very simple generalization of what we did before. Remember, when we talked about dynamics of Gaussian state just for bosons, we really projected our dynamics just by looking at states where we either do not create any excitation, create one, or create two. When we talked about Gaussian state for fermions, we were only looking at creating two excitations, like two fermions on top of the vacuum. So in the case of Polarn transformation, we'll just add one more state where we simultaneously create two fermions in vacuum and an extra phonon, right? And it's kind of reasonable, natural why this comes out, because the Polarn transformation itself, remember, is of this type, right? It's quadratic in fermions, and it's linear in the bosonic operators. So anyway, once you sort of include this, so therefore now when we project, remember we have all this projection into basis vectors, now we just have to introduce an extra basis vectors. And once you add these basis vectors, you get explicit equations on the coefficients of the Polaron transformation. Okay, so this just shows you that we recover, let's say, so if we look at the equilibrium, and we recover results which are perfectly consistent with Monte Carlo study of the Holstein model. So it's known that Holstein model at half filling has charge density wave order parameter. So this kind of dashed line, so this is axis is chemical potential, and this dashed line corresponds to charge density wave order parameter, and the blue line corresponds to the superconducting order parameter. So we see that, okay, we have a first order phase transition from charge density wave state exactly at half filling to superconducting state away from half filling. So again, just good test that things are behaving the way they should. Well, actually for larger coupling, we find something that there seems to be. Well, no, actually, I'm not sure. I think it's finite size effect. We didn't look into detail whether there is really a narrow region where we have a coexistence of both orders. And then just to remind you that that's what we discussed before. So what happens if, let's say, we start changing the value of electron-phonon interactions and we look at dynamics of the order parameter? We saw this Higgs oscillation, right? The fact that the order parameter amplitude was changing in time. So that was really derived using equations that I showed you before. So that was our, and then we did so this was order parameter, color coding of the order parameter as a function of time. And then we do a Fourier transform and we see this fairly bright peak, which corresponds to the Higgs amplitude mode. And then we show, also we sort of went from just simply quenching electron-phonon interaction, which is sort of like a Gedanken experiment, to do what's more, what's closer to experiments, which is parametrically driving phonons, and we still see very similar features of exciting Higgs-like excitations. So another advantage of this variational approach is that you can compute physical responses. So remember, I showed you Keldysh calculations for non-equilibrium electron-phonon systems. So like doing traditional Keldysh approach, okay, not exactly traditional. We had this extra kind of Flaquier addition, but still in the spirit of canonical Kurdish. So this was in a technical language we're only solving for Green's function. This was Dyson's equation. If we want to calculate optical response, we have to solve the so-called Bethe-Salpeter equation. And they just are so hard that we didn't even try. Even Dyson equation was rather difficult to solve. So we didn't even kind of dare to try and calculate optical conductivity. But with variational wave function, it is actually rather straightforward, because all you do, you just apply external field to your system. In this case, it's electric field, and you calculate the current, right? Because it's almost like you're doing numerical experiment, right, within these variational wave functions. And so once you calculate the current, you can then calculate conductivity. And that's, for example, when we saw enhancement of superconductivity, the best way to illustrate it. So in this case, we start with some equilibrium value of the quasi-particle gap. And then we apply a drive, and we see that the quasi-particle gap increases, which indicates enhancement of superconductivity. Okay, and then there are some actually very subtle features, which is, often when like there were other papers which tried to look for this kind of parametric enhancement of superconductivity, but they were only looking at kind of superconducting order parameter in terms of the original order parameter. And they saw that it actually gets suppressed. And in fact, that's also what we find. But the physics is rather simple. It just says that actually our original fermions are not the true degrees of freedom. Our true degrees of freedom are quasi-particles. Right? Remember, these are fermions dressed by phonons. And so what's happening is that once we drive the system, our electrons are dressed more heavier by phonons. And therefore, if I look at the pairing amplitude, okay, so then there is something that corresponds to, let's say, anomalous expectation value of my polarons. But then there is the part which just comes from polaron transformation. That polaron transformation gets larger. So as a result, my order parameter itself, if I just naively define it in terms of fermion, gets suppressed due to heavier polaronic dressing. However, the right way of defining whether we have enhancement or suppression of superconductivity is through these polaronic quasi-particles, electrons dressed in phonons. And that's why we should really calculate a physical observable such as optical conductivity, and we see that the optical conductivity goes up. Okay, so I think it's a good place to stop, though it may not be the exact time, but...
May I ask a couple of questions?
Sure, yes.
Is it possible to see in this framework BCS to BC crossover?
Sure.
If you enhance your phonons.
But with phonons, I see. Sure, it can. I mean, it contains. I think all the physics that you put into the BCS to BC crossovers. So I think the answer is yes. We haven't tried it. Yeah.
Okay. And other question is again about temperature. And comparing different superconducting systems, it's very important to consider the ratio of transition temperature to the superconducting gap at zero temperature. Can you expect to have this? I understand now you have only T equals 0, but...
No, actually, we have results for finite T. I just didn't show them. But so let me at least comment on the general structure. So roughly, the way it works is that, I mean, there are several ways of doing this. Let me tell you about the simplest one. So, at finite temperature, you need to minimize the free energy, which is E minus T times S, right? Entropy. And S is basically trace, rho log rho. And what you notice is that, okay, so how do we think about our rho? So roughly, you can think about our rho as kind of is rho Gaussian, right? Times, let's say, we have this transformation US and US dagger, right? We have the polaron transformation.
But does it somehow affect the...
That's the beauty. So you see, when you put this in, actually this Polaron transformation drops out, and therefore this becomes trace of rho Gaussian log of rho Gaussian. So therefore, actually, and this you can express once you have single, because let's say in equilibrium, we go to a fixed point. If you calculate, okay, I didn't talk about this, but within this formulas, you can also calculate eigenmodes on top of the fixed point. Therefore, you know all the single particle excitation epsilon of k. Once you know single particle excitation, you can calculate rho Gaussian. So there is actually a very similar formalism that you can write, in which you basically have, you can write in kind of flow in imaginary time, again, of the variational parameters. But now you will be minimizing free energy rather than energy. So it's a bit tricky. The reason it gets tricky is that when you're at low temperature, your density matrix has eigenvalues close to 1, and their logs are sort of infinite. This doesn't matter because it will be cancelled by temperature, but numerically it's a bit of a challenge. So we have some results, but we're still working on this. So actually, higher temperature for us is easier than actually really going to lower temperatures. But in principle, this formalism works also at finite temperature. Particularly, you can look at transitions, like competition.
Have you seen a transition?
Yeah, right. Yes.